All right, on paper we were looking at what's the rate of change of f of x equals x cubed near or at x equals 5, and we tried it with a delta x of 1 going from x equals 5 to x equals 6, and we got a forward difference quotient of 91. And then we said, well, how about some smaller delta x's? So we're really concentrating right near 5, and I've got a spreadsheet set up here to say, well, when x goes from 5 to 6, delta x is 1, and actually here I'm computing the 6 based on the previous x and the delta x. That'll save us some time in just a sec. And I'm saying here's x cubed, so I can just fill that down 1 and compute x cubed there, and compute the finite difference quotient here. You don't have to be playing along here, but it's a good thing to imagine what I'm about to type. Okay, ready? Imagine it, and here we go. So new y value minus old y value divided by new x value minus old x value, or I could just divide by delta x there, since that I've already computed that. Either way is fine. So we got that 91 that we said here. And now we want to try a different delta x. I could just type a new one here, but then I'd lose track of what I had there. So I'm going to copy this and change delta x to 0.1 here. And I don't have to do any new formulas. It's all just done for me. And I get a delta x of 70, a finite difference, a forward difference quotient of 76.51. And then I can say, well, let's try another delta x. How about 0.01? And so our forward difference quotient is dropping. We could try it at even another 0.001. So we're getting 5 and something really, really close to 5. And we're getting something that's dropping still. This is lower than that one, but it's not dropping nearly as much as it dropped there. We could say, well, if I really want to concentrate at x equals 5 itself, why don't I just let delta x equals 0? Take a sec to think what's going to happen when I hit enter here. I got an error from Excel. I was doing 5 minus 5 in the denominator, so I got a 0 there, got to divide by 0. It's interesting that the numerator is also 0, so I got 0 over 0, and we'll spend a lot of time in chapter 1 talking about that when we get to chapter 1. There's actually no reason that delta x has to be positive. I could use a negative delta x value, go from 5 backward a little bit, and now I'm getting something slightly less than 75. So we can look at these values and say, what kind of number would I guess would go here based on how the finite forward difference quotient was changing when I use smaller and smaller delta x. So you probably have a guess of what number goes there. It'd be nice to have all these numbers right next to each other so I didn't have to scroll past them. So I'm going to show you a skill right now that is completely not required for our class, but it is a really handy Excel skill. It's called VLOOKUP. So I'm going to say VLOOKUP. I'm going to say look up this delta x number in this big block of cells. And I'm going to, let me try that again. You look up this value in A6 in this big block of cells, and I'm going to lock that reference and say, so it's going to look up these numbers in this first column of the block, and then I want the values from the fourth column on the matching rows. So I want column 4, and I want exact matches for the delta x's. And then I'll paste that down. And sure enough, that looks up each of these numbers in this block of cells and gives me the forward difference quotient. So how is the forward difference quotient changing as delta x gets smaller and smaller close to 0? What number would naturally go right there? That's a question that we answer algebraically with the word limit in chapter 1, but you can probably have a good idea of what's going to go right there. Our next trick is going to be doing something very similar in the computer software Desmos Online, which is another great tool to use in Calc 1.